A very refreshing good afternoon to one and all. It's the Vishi from third year. And on the behalf of ELSOC, the Society of Electrical Department of NIT Hamirpur, we all welcome to the workshop on the topic blockchain technology. I would like to request you all to be active throughout the workshop as we will be conducting a quiz at the end, and the top three winners are going to be awarded with some amazing prizes. And the quiz is going to be live. So stay tuned. Some of you must be unaware of the term blockchain. So, yeah, blockchain is a decentralized ledger of all transactions across a peer to peer network. The blockchain technology creates a digital world that reaches far beyond just the finance and insurance industries. In fact, there are numerous business and governmental sectors which include manufacturing, healthcare, utility, and advertising all use blockchain technology to process different transactions. Next slide. So in this workshop, we will be focusing on the basics of blockchain in Python, then the implementation of the demo coin, and the last section would be including the application of blockchain. Now I would like to hand over the screen to Abhishek to start with the workshop.
Basics of blockchain. Next slide, please. In this section, we are going to learn the necessity of blockchain, the history of blockchain, working procedure, and the importance of digital signature, SHA-256 algorithm, RS algorithm. But first of all, we are going to clear some basic theoretical concept of blockchain. For that, we are going to see a video from Tribhuvan Brown. Next.
What does it mean to have a Bitcoin? Many people have heard of Bitcoin, that it's a fully digital currency with no government to issue it, and that no banks need to manage accounts and verify transactions. And also that no one really knows who invented it. And yet, many people don't know the answer to this question, at least not in full. To get there, and to make sure that the technical details underlying the answer actually feel motivated, what we're going to do is walk through, step by step, how you might have invented your own version of Bitcoin. We'll start with you keeping track of payments with your friends using a communal ledger, and then as you start to trust your friends and the world around you less and less, and if you're clever enough to bring in a few ideas from cryptography to help circumvent the need for trust, what you end up with is what's called a cryptocurrency. What does it mean to have a Bitcoin? Many people have heard of Bitcoin, that it's a fully digital currency with no government to issue it, and that no banks need to manage accounts and verify transactions. And also that no one really knows who invented it. And yet, many people don't know the answer to this question, at least not in full. To get there, and to make sure that the technical details underlying the answer actually feel motivated, what we're going to do is walk through, step by step, how you might have invented your own version of Bitcoin. We'll start with you keeping track of payments with your friends using a communal ledger, and then as you start to trust your friends and the world around you less and less, and if you're clever enough to bring in a few ideas from cryptography to help circumvent the need for trust, what you end up with is what's called a cryptocurrency. You see, Bitcoin is just the first implemented example of a cryptocurrency, And now there are thousands more on exchanges with traditional currencies. Walking the path of inventing your own can help to set the foundations for understanding some of the more recent players in the game, and recognizing when and why there's room for different design choices. In fact, one of the reasons I chose this topic is that in the last year, there's been a huge amount of attention and investment and, well, honestly, hype directed at these currencies. And I'm not going to comment or speculate on the current or future exchange rates, but I think we'd all agree that anyone looking to buy a cryptocurrency should really know what it is. And I don't just mean in terms of analogies with vague connections to gold mining. I mean an actual direct description of what the computers are doing when we send, receive, and create cryptocurrencies. One thing worth stressing, by the way, is that even though you and I are going to dig into the details here, and that takes meaningful time, you don't actually need to know those details if you just want to use the cryptocurrency. Just like you don't need to know the details of what happens under the hood when you swipe a credit card. Like any digital payment, there's lots of user-friendly applications that let you just send and receive the currencies without thinking about what's going on. The difference is that the backbone underlying this is not a bank that verifies transactions. Instead, it's a clever system of decentralized trustless verification based on some of the math born in cryptography. But to start, I want you to actually set aside the thought of cryptocurrencies and all that just for a few minutes. We're going to begin the story with something more down to earth: ledgers and digital signatures. If you and your friends exchange money pretty frequently, paying your share of the dinner bill and such, it can be inconvenient to exchange cash all the time. So you might keep a communal ledger that records all of the payments that you intend to make some point in the future. Alice pays Bob $20, Bob pays Charlie $40, things like that. This ledger is going to be something public and accessible to everyone, like a website where anyone can go and just add new lines. And let's say that at the end of every month, you all get together, look at the list of transactions, and settle up. If you spent more than you received, you put that money in the pot, and if you received more than you spent, you take that money out. So the protocol for being part of this very simple system might look like this. Anyone can add lines to the ledger, and at the end of every month, you all get together and settle up. Now, one problem with a public ledger like this is that anyone can add a line. So what's to prevent Bob from going and writing Alice pays Bob $100 without Alice approving? How are we supposed to trust that all of these transactions are what the sender meant them to be? Well, this is where the first bit of cryptography comes in: digital signatures. Like handwritten signatures, the idea here is that Alice should be able to add something next to that transaction that proves that she has seen it and that she's approved of it. And it should be infeasible for anyone else to forge that signature. At first, it might seem like a digital signature shouldn't even be possible. I mean, whatever data makes up that signature can just be read and copied by a computer, so how do you prevent forgeries? Well, the way this works is that everyone generates what's called a public key-private key pair, each of which looks like some string of bits. The private key is sometimes also called a secret key, so that we can abbreviate it as SK while abbreviating the public key as PK. Now, as the name suggests, this secret key, it's something you want to keep to yourself. In the real world, your handwritten signature looks the same no matter what document you're signing. But a digital signature is actually much stronger, because it changes for different messages. It looks like some string of ones and zeros, commonly something like 256 bits, and altering the message even slightly completely changes what the signature on that message should look like. Speaking a little more formally, producing a signature involves a function that depends both on the message itself and on your private key. The private key ensures that only you can produce that signature, and the fact that it depends on the message means that no one can just copy one of your signatures and then forge it on another message. Hand in hand with this is a second function used to verify that a signature is valid. And this is where the public key comes into play. All it does is output true or false to indicate if this was a signature produced by the private key associated with the public key that you're using for verification. I won't go into the details of how exactly both these functions work, but the idea is that it should be completely infeasible to find a valid signature if you don't know the secret key. Specifically, there's no strategy better than just guessing and checking random signatures, which you can check using the public key that everyone knows. Now think about how many signatures there are with a length of 256 bits. That's 2 to the power of 256. This is a stupidly large number. To call it astronomically large would be giving way too much credit to astronomy. In fact, I made a supplemental video devoted just to illustrating what a huge number this is. Right here, let's just say that when you verified that a signature against a given message is valid, you can feel extremely confident that the only way someone could have produced it is if they knew the secret key associated with the public key you used for verification. Now, making sure that people sign transactions on the ledger is pretty good, but there's one slight loophole. If Alice signs a transaction like Alice pays Bob $100, even though Bob can't forge Alice's signature on a new message, he could just copy that same line as many times as he wants. I mean, that message-signature combination remains valid. To get around this, what we do is make it so that when you sign a transaction, the message has to also include some sort of unique ID associated with that transaction. That way, if Alice pays Bob $100 multiple times, each one of those lines on the ledger requires a completely new signature. Alright, great. Digital signatures remove a huge aspect of trust in this initial protocol. But even still, if you were to really do this, you would be relying on an honor system of sorts. Namely, you're trusting that everyone will actually follow through and settle up in cash at the end of each month. What if, for example, Charlie racks up thousands of dollars in debt and just refuses to show up? The only real reason to revert back to cash to settle up is if some people, I'm looking at you, Charlie, owe a lot of money. So maybe you have the clever idea that you never actually have to settle up in cash as long as you have some way to prevent people from spending too much more than they take in. Maybe what you do is start by having everyone pay $100 into the pot, and then have the first few lines of the ledger read, Alice gets $100, Bob gets $100, Charlie gets $100, etc. Now, just don't accept any transactions where someone is spending more than they already have on that ledger. For example, if the first two transactions are Charlie pays Alice $50 and Charlie pays Bob $50, if he were to try to add Charlie pays you $20, that would be invalid as if he had never signed it. Notice, this means that verifying a transaction requires knowing the full history of transactions up to that point. And this is, more or less, also going to be true in cryptocurrencies, though there is a little room for optimization. What's interesting here is that this step removes the connection between the ledger and actual physical US dollars. In theory, if everyone in the world was using this ledger, you could live your whole life just sending and receiving money on this ledger without ever having to convert to real US dollars. In fact, to emphasize this point, let's start referring to the quantities on the ledger as ledger dollars, or LD for short. You are, of course, free to exchange ledger dollars for real US dollars. For example, maybe Alice gives Bob a $10 bill in the real world in exchange for him adding and signing the transaction Bob pays Alice 10 ledger dollars to this communal ledger. But exchanges like that, they're not going to be guaranteed by the protocol. It's now more analogous to how you might exchange dollars for euros or any other currency on the open market. It's just its own independent thing. This is the first important thing to understand about Bitcoin, or any other cryptocurrency. What it is a ledger. The history of transactions is the currency. Of course, with Bitcoin, money doesn't enter the ledger with people buying in using cash. I'll get to how new money enters the ledger in just a few minutes. But before that, there's actually an even more significant difference between our current system of ledger dollars and how cryptocurrencies work. So far, I've said that this ledger is in some public place, like a website where anyone can add new lines. But that would require trusting a central location, namely, who hosts the website, who controls the rules of adding new lines. To remove that bit of trust, we'll have everybody keep their own copy of the ledger. Then when you want to make a transaction, like Alice pays Bob 100 ledger dollars, what you do is broadcast that out into the world for people to hear and to record on their own private ledgers. But unless you do something more, this system is absurdly bad. How could you get everyone to agree on what the right ledger is? When Bob receives a transaction, like Alice pays Bob 10 ledger dollars, How can he be sure that everyone else received and believes that same transaction? That he'll be able to later on go to Charlie and use those same 10 ledger dollars to make a transaction? Really, imagine yourself just listening to transactions being broadcast. How can you be sure that everyone else is recording the same transactions and in the same order? This is really the heart of the issue. This is an interesting puzzle. Can you come up with a protocol for how to accept or reject transactions and in what order, so that you can feel confident that anyone else in the world who's following that same protocol has a personal ledger that looks the same as yours? This is the problem addressed in the original Bitcoin paper. At a high level, the solution that Bitcoin offers is to trust whichever ledger has the most computational work put into it. I'll take a moment to explain exactly what that means. It involves this thing called a cryptographic hash function. The general idea that we'll build to is that if you use computational work as a basis for what to trust, you can make it so that fraudulent transactions and conflicting ledgers would require an infeasible amount of computation to bring about. Again, I'll remind you that this is getting well into the weeds beyond what anyone would need to know just to use a currency like this. But it's a really cool idea, and if you understand it, you understand the heart of Bitcoin and of other cryptocurrencies. So first things first, what's a hash function? The inputs for one of these functions can be any kind of message or file, it really doesn't matter. And the output is a string of bits with some kind of fixed length, like 256 bits. This output is called the hash or the digest of the message, and the intent is that it looks random. It's not random, it always gives the same output for a given input. But the idea is that if you slightly change the input, maybe editing just one of the characters, the resulting hash changes completely. In fact, for the hash function that I'm showing here, called SHA-256, the way the output changes as you slightly change that input is entirely unpredictable. You see, this is not just any hash function, it's a cryptographic hash function. That means it's infeasible to compute in the reverse direction. If I show you some string of ones and zeros and ask you to find an input so that the SHA-256 hash of that input gives this exact string of bits, you will have no better method than to just guess and check. And again, if you want a feel for how much computation would be needed to go through 2 to the 256 guesses, just take a look at the supplement video. I actually had way too much fun writing that thing. You might think that if you just really dig into the details of how exactly this function works, you could reverse engineer the appropriate input without having to guess and check. But no one has ever figured out a way to do that. Interestingly, there's no cold, hard, rigorous proof that it's hard to compute in the reverse direction. And yet, a huge amount of modern security depends on cryptographic hash functions and the idea that they have this property. If you were to look at what algorithms underlie the secure connection that your browser is making with YouTube right now, or that it makes with your bank, you will likely see the name SHA-256 show up in there. For right now, our focus will just be on how such a function can prove that a particular list of transactions is associated with a large amount of computational effort. Imagine someone shows you a list of transactions, and they say, "Hey, I found a special number so that when you put that number at the end of this list of transactions and apply SHA-256 to the entire thing, the first 30 bits of that output are all zeros." How hard do you think it was for them to find that number? Well, for a random message, the probability that a hash happens to start with 30 successive zeros is 1 in 2 to the 30, which is about 1 in a billion. And because SHA-256 is a cryptographic hash function, the only way to find a special number like that is just guessing and checking. So this person almost certainly had to go through about 1 billion different numbers before finding this special one. And once you know that number, it's really quick to verify. You just run the hash and see that there are 30 zeros. So in other words, you can verify that they went through a large amount of work, but without having to go through that same effort yourself. This is called a proof of work. And importantly, all of this work is intrinsically tied to the list of transactions. If you change one of those transactions, even slightly, it would completely change the hash. So you'd have to go through another billion guesses to find a new proof of work, a new number that makes it so that the hash of the altered list together with this new number starts with 30 zeros. So now think back to our distributed ledger situation. Everyone is there broadcasting transactions, and we want a way for them to agree on what the correct ledger is. As I said, the core idea behind the original Bitcoin paper is to have everyone trust whichever ledger has the most work put into it. The way this works is to first organize a given ledger into blocks, where each block consists of a list of transactions together with a proof of work. That is, a special number so that the hash of the whole block starts with a bunch of zeros. For the moment, let's say that it has to start with, 60 zeros, but later we'll return back to a more systematic way you might want to choose that number. In the same way that a transaction is only considered valid when it's signed by the sender, a block is only considered valid if it has a proof of work. And also, to make sure that there's a standard order to these blocks, we'll make it so that a block has to contain the hash of the previous block at its header. That way, if you were to go back and change any one of the blocks, or to swap the order of two blocks, it would change the block that comes after it, which changes that block's hash, which changes the one that comes after it, and so on. That would require redoing all of the work, finding a new special number for each of these blocks that makes their hashes start with 60 zeros. Because blocks are chained together like this, instead of calling it a ledger, it's common to call it a blockchain. As part of our updated protocol, we'll now allow anyone in the world to be a block creator. What that means is that they're going to listen for transactions being broadcast, collect them into some block, and then do a whole bunch of work to find a special number that makes the hash of that block start with 60 zeros. Then once they find it, they broadcast out the block that they found. To reward a block creator for all this work, when she puts together a block, we'll allow her to include a very special transaction at the top of it, in which she gets, say, 10 ledger dollars out of thin air. This is called the block reward, and it's an exception to our usual rules about whether or not to accept transactions. It doesn't come from anyone, so it doesn't have to be signed. And it also means that the total number of ledger dollars in our economy increases with each new block. Creating blocks is often called mining, since it requires doing a lot of work, and it introduces new bits of currency into the economy. But when you hear or read about miners, keep in mind that what they're really doing is listening for transactions, creating blocks, broadcasting those blocks, and getting rewarded with new money for doing so. From the miner's perspective, each block is kind of like a miniature lottery, where everyone is guessing numbers as fast as they can until one lucky individual finds a special number that makes the hash of the block start with many zeros, and they get the reward. For anyone else who just wants to use this system to make payments, instead of listening for transactions, they all start listening just for blocks being broadcast by miners and updating their own personal copies of the blockchain. Now, the key addition to our protocol is that if you hear two distinct blockchains with conflicting transaction histories, you defer to the longest one, the one with the most work put into it. If there's a tie, just wait until you hear an additional block that makes one of them longer. So even though there's no central authority and everyone is maintaining their own copy of the blockchain, if everyone agrees to give preference to whichever blockchain has the most work put into it, we have a way to arrive at decentralized consensus. To see why this makes for a trustworthy system, and to understand at what point you should trust that a payment is legit, it's actually really helpful to walk through exactly what it would take to fool someone using this system. Maybe Alice is trying to fool Bob with a fraudulent block. Namely, she tries to send him one that includes her paying him 100 ledger dollars, but without broadcasting that block to the rest of the network. That way, everyone else still thinks that she has those 100 ledger dollars. To do this, she would have to find a valid proof of work before all of the other miners, each working on their own block. And that could definitely happen. Maybe Alice just happens to win this miniature lottery before everyone else. But Bob is still going to be hearing the broadcasts made by other miners. So to keep him believing this fraudulent block, Alice would have to do all of the work herself to keep adding blocks on this special fork in Bob's blockchain that's different from what he's hearing from the rest of the miners. Remember, as per the protocol, Bob always trusts the longest chain that he knows about. Alice might be able to keep this up for a few blocks if just by chance she happens to find blocks more quickly than the rest of the miners on the network all combined. But unless she has close to 50% of the computing resources among all of the miners, the probability becomes overwhelming that the blockchain that all of the other miners are working on grows faster than the single fraudulent blockchain that Alice is feeding to Bob. So, after enough time, Bob's just going to reject what he's hearing from Alice in favor of the longer chain that everyone else is working on. Notice, that means that you shouldn't necessarily trust a new block that you hear immediately. Instead, you should wait for several new blocks to be added on top of it. If you still haven't heard of any longer blockchains, you can trust that this block is part of the same chain that everyone else is using.
So, I hope you hear the video all completely. अभी यहाँ से हम लोग बेसिकली पाइथन की बेसिक्स को सबसे पहले जानेंगे. So I will start with the variable. First of all, Python is an interpreted language, and it is a dynamic language. I hope you are quite understandable about the Python. And first of all, integer variable x is equal to 16. Now after that, string variable, float numbers. We can run this code by ओके. तो हम पहले स्टार्ट करते हैं डेमो पॉइंट की टेस्टिंग से. जैसा कि अपने वीडियो में देखा, सेम चीज हम लोग यहाँ पर एज अ डेमो कॉइन की तरह बनाने वाले हैं. तो फॉर दिस आई होप लेट्स स्टार्ट विथ अ न्यू फाइल. इसको साथ में करना हो स्टार्ट कर सकते हैं. .py. फर्स्ट ऑफ ऑल वी नीड 3 लाइब्रेरीज, है ना. पहली हैशलिप, ये यूज होगी SHA-256 और RSA एल्गोरिथम के लिए. एक लाइब्रेरी अलग से RSA के लिए एंड एक रैंडम स्टैंडर्ड लाइब्रेरी पाइथन की. उसके बाद हमें 4 क्लासेस बनानी है. फर्स्ट क्लास ट्रांजैक्शन, सेकंड क्लास चेन, एंड थर्ड क्लास ब्लॉक, फोर्थ क्लास वैलेट. किसी को कोई डाउट हो सकता है तो पूछ सकता है बीच में ही. तो स्टार्ट करते हैं. सबसे पहले ट्रांजैक्शन क्लास. ट्रांजैक्शन क्लास नॉर्मल ट्रांजैक्शन मनी. फॉर ट्रांजैक्शन क्लास वी नीड 3 थिंग्स. सबसे पहले चीज क्या चाहिए? सेंडर, जिसने मनी भेजी. रिसीवर, जिसको मनी मिली. एंड अमाउंट, जितनी अमाउंट में मनी चली गई, भेजी गई. सबसे पहले हम उसको उनकी अपनी प्रॉपर्टीज पे शो कर देंगे. आफ्टर दैट वी मेड अ न्यू फंक्शन गेट ट्रांजैक्शन. द वर्क ऑफ दिस फंक्शन इज टू सीरियलाइज ऑल द थिंग्स इनटू अ स्ट्रिंग. After transaction section, we are going to meet a different next class known as chain. It contains a chain variable with a list, a pool section for mining, a count variable, and a number variable. They both are used for mining section. After that, add the pool. We'll discuss this later on. First of all, add block method. This method used to add block, but before adding block, we have to first define the block. So we are defining a class named blocked. It contains two argument, previous block hash and a transaction list. First, we set up the properties. After that, we will join. This is a list function, if you know. We will join the list with the previous hash block and create a random number known as nouns. After that, we create a hash function. This is uses hashlib official library SHA-256 method to hash the incoming transaction. For testing, let us increment all the codes. Let define a transaction. I determined the sixth transaction, demo transaction, and the coin name demo coin just for example purpose. If you run the code, then here what you get. Okay. There is an issue. This is broken. Good. Oh, sorry. Because here it is. Now, if you run the code, the blockchain deploy, it is generated the hash function of this block, which is currently added to the blockchain, and give the message that one block is added. If we can add more blocks like this t2 dot get transaction. If now see what is the point of noticing. What is we got notice if we change this is first block added, this is second block added. If we change anything in the first block, let's see anything in the first block. Here transaction 2 and transaction 5 is in the first block. Transaction 2. If we change anything in the first block, the whole hash function is changing. Complete. Just a single changes complete the hash function. Not only first but second also. After that, I implemented something, a wallet, just for show. As you see the video, there is a two keys, public keys and private keys. They are both generated with the RC algorithm, and we can use a library named RSA. So first we imported the library, create a valid class, and this class contains three variables. Uh, RSA.new keys. It takes an input number which determine the length of the key, private public both. First public key, let's generate public and private key. We assign the public and private key to their class variables. After that, and there is signature function. We can take it. Let me create a valid first. Bob. I'm going to see public. So this is the public key. This whole. These keys are available for if you ever if you go and if find exchanges for trading, and you create account, you get both public and private key, and your public key is completely public. So this is a public key you can generate here, and there is another key named private key which is not used for sharing purpose. This is the private key. What we are doing here, we can encode the message by using these keys. Let's use the sign function, signature function. Let's see. New transaction, get transaction. Private key of Bob for signing. In hash method, we are using here MD5. This sign value. At the same time, if you want to verify them, then if right. Zero. Verify. Signature. So, keep up. Signature. If any error occurs, verification failed. Let's run this code. So here it is. These are the sign method and sensor. If anyone want the code, if anyone have a doubt for this code, you can ask the question. Source code. Source code is available for in GitHub at the end of the workshop. We will give you a GitHub link. From there, you can download the source code. without recording about even 50% conversation. Next slide. Dipesh, next. Next. Application product.
Hello. So now we will learn about application of blockchain. Next slide. So application of blockchains are money transfer and payment processing, supply chain monitoring, protection of royalty and copyright, digital voting, transfer of real estate, land and auto title, unchangeable data backup, food safety, and digital IDs. So let's take an example of digital voting. In election, we usually have a central authority that records, count, and check all the votes. And with blockchain, the process is decentralized. So everyone can hold a copy of full voting record on their own device. The data is encrypted to protect the identity of individual voters so that false votes cannot be added and the historical record cannot be changed. Because everyone hold a copy and can check that all votes comply with the rules and are counted properly. Next slide.
Now, coming to the major fields of blockchain. First, cryptocurrency. Cryptocurrencies are digital currencies like Bitcoin, Ethereum, or Litecoin that can be used to buy goods and services. Unlike cash, crypto uses blockchain to act as both a public ledger and enhanced cryptographic security system. So online transactions are always recorded and secured. Second, Web3. Web3 is the latest buzz in the market. Web3 enables users and developers to use decentralized blockchain technology. Now, NFTs. You have heard a lot of NFTs about NFTs. NFTs are digital items that can be bought and sold using blockchain technology. However, they are not fungible, making them a different type of asset, one that is based on value and popularity. Next slide, please. Now, let's discuss advantages and limitations of blockchain, starting with the advantages that makes blockchain trustable. First, enhanced security. Users' data is sensitive and crucial. By creating a record that can't be altered and is encrypted end to end, blockchain helps prevent fraud and unauthorized activity. Second, greater transparency. Without blockchain, each organization has to keep a separate database. Because blockchain uses a distributed ledger where all transactions are immutably recorded, all network participants can see the same information at the same time, providing full transparency. Third, instant traceability. With blockchain, it is possible to share data about provenance directly with consumers. Fourth, increased efficiency and speed. Traditional paper heavy processes are always time consuming, prone to human error, and often requires third party mediation. By streamlining these processes with blockchain, transactions can be completed faster and more efficiently. Last, automation. Transactions can even be automated with smart contracts, which increase your efficiency and speed the process even further. Now, let's discuss the limitations of blockchain. First, lack of awareness. There is a lot of discussion about blockchain, but people do not know the true value of the blockchain and how they could implement it in different situations. Second, Key management. As we know, blockchain is built on cryptography, which implies that there are different keys, such as public keys and private keys. When you are dealing with a private key, then you are also running the risk that somebody may lose access to your private key. Third, immutability. In this, we cannot make any modification to any of the records. It is very helpful if you want to keep the integrity of a record and make sure that nobody ever tampers with it. But immutability also has a drawback. You can't change the data once added to blockchain. Fourth, scalability. Blockchain like Bitcoin has consensus mechanisms which require every participant nodes to verify the transaction. It limits the number of transactions a blockchain network can process. Last, consensus mechanism. In the blockchain, we know that a block can be created in every 10 minutes. It is because every transaction made must ensure that every block in the blockchain network must reach a common consensus. Depending on the network size and the number of blocks or nodes involved in a blockchain, the back and forth communication involved to attain a consensus can consume a considerable amount of time and resources. Constant efforts are made to resolve these limitations. Over to Namrita.
Thank you, everyone. Hope you all have enjoyed this workshop. I hope this workshop has given you an astounding insight into about blockchain technology. It's time for Q&A session. So if you have any doubt, you can put your queries in the comment box. After that, we will start live quiz. The winners will get the certificates and prize. So all the best, everyone. The link is in description. You can register yourself for the quiz. You can register yourself for quiz also, and there is a question in chat box: which branch choose black blockchain? Any branch can choose blockchain, like it's about your interest and about your what you want regarding that. The participants are registering for the quiz. We'll start the quiz in short. Unable to join? Please share the link in chat box again. You just need to write your name and just have to join the quiz. You need not any enter code for the quiz. एक minute. Code is 781348. 781348. I think we can start the quiz now. There are total number of 38 participants. Okay, we'll start at 3:55. Just wait for 2 minutes. If actually the number of participants is increasing, so we are waiting everyone to join the quiz. You will get the certificate, and there is prize money also, like a prize you will get. We'll tell you what prize you'll get. And I will request the one who will be the winners top 3. I request you to send a message on our Instagram page, ELSOC underscore at NITH. DM your names, top 3 winners. So I think we can start now. There are 48 participants. So let's start with the quiz. First question is, what does a block in a blockchain have? Header and digital ledger, bitcoins and inputs, transition bitcoins, headers and transition. There are total of 10 questions, and you will get 20 seconds to answer each question. The correct answer is header and transition. 26% of you has given the right answer. Next question. We'll see the leaderboard. Aradhya Kapoor is at the top, then Prakhar Pratyush and Akhileshwar. The second question is, which of the following records are not present in the blockchain database? Block records, transitional records, both A and B, or none of these? You have 6 seconds to answer this. Correct answer is none of these, and 47% of you has given the right answer out of 32. Leaderboard. Leaderboard has been changed. Now Akhileshwar is at the top. So, next question. Dash hosts the software needed for transaction, initiation, validation, mining, block creation, and smart contract execution. Your options are external account, EVM, Ethereum full node, smart contract. 2 seconds are remaining to answer. Correct answer is Ethereum full node. Or now we can go to leaderboard. Aradhya, try next question. Oh, now Jasjot is at the top. Congrats, Jasjot. Like leaderboard is changing at very fast pace. So Aradhya, don't lose your hope. Just try to do that. Okay, next question is, which of the following is not a cryptographic algorithm? Tophofish, 5DES, Blowfish, RSA. Correct answer is 5DES, or 29% of you has given the right answer, and 35 out of 48 has given the answer. Leaderboard. Judge shows Just Jodh is still at the top, then Akhileshwar, then Rahit. Keep going, guys. What type of hash function is used when there is a variable number of items to be hashed, such as the many states change in a block? And your options are tree structural hash, simple hash, complex hash, and ether. So 2 seconds are remaining to answer this question. Correct answer is tree structured hash, and 58% of you has given the right answer. Nice. This is thing. Oh, welcome back, Akhileshwar. You are again at the top. Congrats. Next question. Still 5 questions are remaining. Leaderboard can change at any point of the time. What is immutability? Running without the concept of human trust. Maturity of the node needs to come to a consensus. Data in a blockchain cannot be tampered with. P2P digital leader of transition. Correct answer is data in a blockchain cannot be tampered with. 32 of you has given the answer, out of which 59% has given the right answer. Leaderboard. Akhileshwar is at the top. He has given 6 out of 6 correct questions. Jasjot is at second position. He has given 5 out of 6. Five correct answer out of 6. Akansh Verma is at third position. Okay, next question. Transaction 0 in every block of the Bitcoin blockchain is for paying the miner fees, does not have any input UTXO, call the Coinbase transaction, all of the above. Come on, guys. Till now, 30 has given the answer. 33 of you has given the answer. All of the above. 58% of you has given the right answer. Leaderboard. Akhilesh for 7 out of 7 points. So 5 out of 7 points. Okay. Next question. Right, there is also there. Who receive, aggregate, validate, and execute transactions? Miners nodes, smart contract, light wallets, Ethereum full node. Miner nodes is the correct answer, and 80% of you has given the right answer out of 39. So leaderboard. Akhleshwar is at the top. Next question is the transaction Merkle tree root value in a Bitcoin block is circulated using hash of transactions, previous block's hash, number of transaction, none of the above. I hope you are finding the questions interesting. And the correct answer is hash of transactions. 38 out of 49 has given the right answer, has given the answer. Last question. Which of the purpose of a nuisance follows nouns? A hash function prevents double spending, send information to the blockchain network. 5 seconds are remaining. Come on, guys. 36, 30. Okay. 39 of you has given the answers, and correct answer is prevents double spending. And it's time to see the leaderboard. So Jasjot has won the quiz. He has given 8 out of 10 correct answers, 8 correct answer out of 10 questions. Then Akhleshwar and then Rahite. Jasjot has given the question answer in 2 minutes 15 seconds. Akhleshwar 2 minutes 29 seconds. And Rahite 2 minutes 11 seconds. But he has given only 7 out of 10 correct, 7 correct answers out of 10 questions. So I request 3 of you to send us your to DM us on our Instagram page ELSOC_NITH. Now we would like to conclude this workshop. Thank you all who all have been participated in the quiz. Thank you so much.